So going back, this is in, I think, chapter 3 of last semester, but we use an equation that relates acceleration and displacement to AD equals v final squared minus v initial squared. We can substitute in this equation. Acceleration equals force over mass, Newton's second law. Because there's acceleration here, we can put that in to this equation. And that will relate force, mass, and velocity. So we can put that in there. And when we do that, we now get 2f over m times displacement equals v final squared minus v initial squared. We can divide everything by 2. To get rid of the 2 on this side. And so that gives us f over m times d. We can just rewrite this as 1/2 times vf squared and 1/2 times vi squared. Do you have your notes, Santiago? Now you can multiply both sides by m to get rid of the mass in the denominator. So the m will cancel out on the left-hand side. We're going to multiply this side by m. I'll just write it up here in the top. You'll have the top one down. Okay, so this gives us f times d, and then we'll distribute the m to both terms on the right-hand side. So we get 1/2 mv final squared minus 1/2 mv initial squared. Does that look familiar to you? The 1/2 mv squared from yesterday? What did you see yesterday that looked like that? Kinetic energy. So that's the equation for kinetic energy. What is this telling you? Well, if this is v final, that's v initial. This is really kinetic energy final minus kinetic energy initial, right? Because that's how you find kinetic energy, 1/2 mv squared. So if you're doing 1/2 v final squared, that's your final kinetic energy, 1/2 mv squared initially. So you with me so far on this? So that's the same thing as saying that the change in kinetic energy, right? Because change in is always final minus initial, right? So if you're doing final kinetic energy minus initial, that's the same thing as the change in kinetic energy. So what we're saying is that force times d is equal to the change in kinetic energy. Where did you see force times displacement from yesterday? Hey, Becky, in work, right? So that's what this is saying too. So one equation you could use would be this, which says force times displacement equals the change in kinetic energy. Or you can say work is equal to the change in kinetic energy. Like you saw yesterday. So that equation from yesterday. So that's just a derivation, which means it just shows you how we get an equation from other equations. So we just combine a few equations in order to get this equation. Now, which one do you use in homework? Well, it depends on what you've been given. Sometimes this equation would be easier for you to use. Other times it would be this one. It just depends on what information you've been told and which information you need. Okay, so we talked yesterday about joules and what they represent. Energy can be transferred to the object or to the surroundings? So it can go both ways. What can happen is you could have the world, the atmosphere, do work on an object, in which case energy goes from the atmosphere or the environment to the object, or the object gives energy to the environment, to its surroundings. So the first way would be external world does work on the object, which we call the system. So when we say system, we really mean object. So the book might just say system, but when they say system, they mean the object of interest. You know, like we're looking at, you know, a hockey puck going on the rink. The hockey puck is the system. It's what we're looking at. But it can be the other way too, where you can have the system doing work on the surroundings. System, which is the object, can also do work on the surroundings. So what we would say about the first situation, the world does work on the system. The external world is losing energy. System gains energy. So that's for the first condition, that when the external world does work on a system, the world is giving energy to the system. And it's just like with money. You know, you can't make money out of nothing. You either have money or give away to somebody else, but that money is not created. It's only transferred between two people. So if I give money to somebody else, you know, I've lost, say, $20, but somebody else has gained $20. It's always a zero sum where whatever I've lost, somebody else has gained. Same thing here. So if the world is giving something, you know, say that you have this system, which is a box, and the surroundings gives 50 joules of energy to the box, that means that the surroundings has lost 50 joules, but the box has gained 50 joules. So that would be what the condition 1 says, where the environment gives energy to something. So the object gains that energy, the world loses the energy. And then condition number 2 is just the opposite. So in this case, the system loses energy. The system gives energy to the surroundings. So condition 2, we just see the opposite, where, you know, the object would have lost energy, let's say 50 joules again, but the environment has gained that energy. So usually we talk about work, we usually talk about what the object does. So what we would say for this one is that the object has lost energy, so we call this negative work. Because the system has lost energy. Example of this would be sliding, a book across the table, and the book loses speed. It loses energy as it goes across the table. So the table in the air around it is taking energy off the book, and as it does it, the book slows down. And so the book being slid across the table and stopping has negative work done on the book because the book loses that energy.
Is negative work only for number 2?
Yes. Well, negative work for the system, right? So, and we define work usually as what the system undergoes. And so, yes, so number 2, negative work would be when the system would lose energy. Positive work would be for number 1, where you have the system gain energy. Now we can think of it in terms of the environment losing and gaining energy, but usually we think of it as the system, the object we're looking at, gaining or losing energy. And so work, by this definition, is just movement of energy from one thing to another thing. That's the best way to think about work in this chapter, is energy being moved between objects. So work is a transfer of energy. And as we saw in the equation I showed you today, work results in a change in speed. Now think about this example. You have the sun pulling a planet into itself. So the sun in the middle. And you have Earth in orbit out here. And it rotates. How does the sun pull in the Earth? What direction is the sun's force? So the Earth right here experiences a force in what direction? That's right, towards the sun. So we would draw the force perpendicular to the circle. So wherever the Earth is, to draw it very straight, you would have the force vector pointing towards the sun's core, perpendicular to the Earth's velocity. So the velocity of the Earth is tangent to the circle. That's the Earth's velocity. So if you were to have the sun disappear for some reason, and the sun just one day disappears, what would happen to the Earth? Well, just keep on going this direction. Like it would just follow this red line. So the sun disappeared and just vaporized. The Earth would just go this way. It would just follow its velocity because that's its true velocity. Now, why does it go in a circle though? Because everywhere along here, wherever it is, let's say the Earth is up here at the very top. The sun pulls it in right here. So that's the force of the sun exerting the Earth. Now, the sun's velocity, or the Earth's velocity up here, would be this direction, tangent to the circle. And that's what we'd see at any point along here. We would see the Earth going in a line, tangent to the circle for the velocity, but the force going towards the sun's core. So notice the angles of the force versus the speed. The angles are perpendicular to each other. You have one dimension where the velocity is, a different dimension where the force is. They don't coexist. They don't affect each other. Yes.
So the sun all of a sudden stopped having that force on the Earth, with the Earth gaining velocity?
It would just stay at same speed because there's no additional force, right? In order to change the speed to make it go faster, you need an additional force. So, and the force the sun exerts is not in the same dimension as its velocity. So if the sun were to exert a force in this dimension, then it would change its speed. But because the sun's force is in this dimension, not in the speed dimension, it has no effect on Earth's speed. So Earth had that speed when it was first created. When it was created, it had that speed to begin with. The sun didn't give it that speed. It's maintained that speed since that day of creation. So if the sun were gone, the sun would change the direction of the Earth, but not the speed of the Earth. So that's the key point to keep in mind here, that particular forces can change the direction, but not the speed of objects. So that's what the sun can do. It can change the direction of Earth, which it does, but the Earth's speed stays constant. It goes about 70,000 miles per hour around the sun, and it doesn't really change very much. So perpendicular forces will change the direction, but not the speed. So based on that, does the sun do work on the Earth? Is there work being done on the Earth? Yes.
Yes.
And so how do we see work being done on the Earth?
Change in motion.
Change in motion? So is it changing its speed though? It's changing its direction, but is it changing its speed? Right. Now, this one's a little bit tricky because it is changing its direction, so its velocity is changing, but is its speed changing? So its velocity is changing, not its direction, but not its magnitude, so the magnitude doesn't change. Let's look back at the equation for work. Work is equal to the change in kinetic energy, which is equal to 1/2 mv squared final minus 1/2 mv squared initial. So we could put in, velocity can be negative or positive, right? Based on this direction. But when you square it, it all becomes positive. So when we square velocity, we're dealing only with the magnitudes of the velocity or the speed. So kinetic energy would only change if the speed changes. Based on that, work is done only when the speed changes. Right, so there is an acceleration, and there's always a constant change in velocity, but there's not a change in the magnitude of it. That's right. Yeah, the result is what makes it work or not. So you can have a force exerted on something, because the sun exerts a force on the Earth, but that force does not make it change its speed. And because there's no change in its speed, we'd say no work is done on the Earth. So work is done only when the speed changes. If you see no change in speed, no work is done. So, you could press against a wall, and if the wall doesn't move, you've done no work on the wall. You might be really tired. If you press against a wall really, really hard for a while, you might feel really tired. You might be sweating. You might have really put in a lot of work, you feel like, into the wall. But if the wall does not move, scientifically, you did no work on the wall. Or you might be studying for a test, be studying, reading a book, taking notes, and you'll be really tired after you've done that for a few hours. But you have done no work scientifically because you have not made any movements. Work in a scientific sense involves changing speed. And so perpendicular forces result in no work because those do not change the speed of an object, only the direction. So perpendicular forces do not result in work. So we look so far at work done linearly, in a straight line, force being applied in a straight line. But lots of times we apply force at an angle, not in a straight line. So if you were to apply a force, this box on the ground, for example, maybe you're up here. That's a weird person. Try again. And so the box is kind of at your waist. Your force you're applying would be at an angle if you're pushing like that. And so the force vector would look like this. Now, what does that mean as far as the magnitude of force? Well, you have two different dimensions that you're applying force in. And so we need to think of it in terms of the y and the x dimension. So you have a downward movement, and you also have a forward movement. And so you'd have F sub x, your horizontal force. We also would have F sub y, a downward force. And so you're applying force in two dimensions. You're pushing down on the box, you're also pushing the box forward. Now, what dimension actually does work in this case? The downward force or the horizontal force? F sub x or F sub y? Which one actually does work on the box? Very good, F sub x. How do we know that it's F sub x? Very good. Because you can press down on a box, and pressing down on something is staying in place, right? I mean, the box doesn't go through unless the box went through the floor. So if you had like a really old building, press down the box, the floor caved in, then you'd be doing work downward. But as long as the box just stays on the ground, there's no work being done vertically. The box just stays in place vertically. The work that's being done, if you're pushing the box forward, we're assuming the box goes this way, the force that's being done on the box that makes it move is the horizontal force. So the other force is just wasted. So you're downward pushing. So you'd be more efficient if you were to apply your force only this way. So if you were to, go down, scooch down and apply force just this direction, you would be more efficient than pushing the box the way that person's pushing the box. Now, how do we know how much force is being done in each dimension? You'd use sine and cosine to figure out how much force is being done in the x dimension and the y dimension. So let's just say that this person, for the magnitude of the force, he's applying a force of 250 newtons. So that's the magnitude of force. But how much is being done in the x dimension and the y dimension? Well, it's split. 250 newtons of force is split between the two dimensions. So we would need to find out for force in the x dimension, we would need to multiply that by cosine. So F sub x would equal magnitude, 250 newtons, times cosine, of the angle that you're pushing the box with. And then the force in the y dimension, your magnitude of the force times sine of the angle you're pushing the box with. So let's just say that this angle that we're using looks close to being 45 degrees. So we'll call that 45 degrees. You have to be told the angle, but we'll just say, just to make it easier, that it's 45-degree angle from this red line, which is the force he's applying, to straight up. But you'll be told in the homework problems what the angle is. So this case, we're told 45-degree angle that he's using. So we can add in 45 degrees to these. And we would just multiply the magnitude times cosine of 45 and sine of 45 to get the amount of force in those dimensions. Can somebody find those for me really fast? 250 times cosine of 45. Be sure that, again, that you're using degrees for physics, not radians. 176. Okay. And what's nice about 45 degrees is that once you get one, you get the other one. They're both the same. So 176 would be the number for both x and y. So that's how much force is being applied in each dimension. Now let's say instead you change the angle and that you're now applying a force instead of 45 degrees. The force is, say, like this. So the red line is your force direction. What angle would that be? Well, you have to be told about, again, but let's say it's 25 degrees. So let's try this again, but instead the angle is 25 degrees. So f of x would be found by doing 250 times cosine of 25 degrees, f sub y, 250 times sine of 25 degrees. Somebody tell me what those are. Yeah. Okay, 226, and you said 105? Okay. So we know about these ones. Yeah, that's right. And that's what you expect, right? I mean, which one is greater? Yeah. That's right, and that would make sense, right? Because you see that the direction that you're pushing this box is mostly horizontal. And so there should be more force horizontally, because the extent of your force is mostly going that way. There isn't a whole lot of downward force. So you'd be more efficient. You would move the box better at this angle because you're going to apply more force with this angle instead of that angle. Yeah. 180 degrees. So let's try and see what that looks like. Okay, so let's say you have this box and you want it to go that way. Your force, this would be the best way to put it, right? I just have your force like that. Is that 180 degrees? Well, it's in the same direction, right? So we call that not 180, but 0. So you'd call that 0 degrees in that way. So this would be an angle of 0 degrees. And that would give you the most force horizontally. Now, what about 180, like you said? What would that look like? So if you want the box to go this way, your force would have to actually be directed this way. From here to here, that's 180 degrees. What would that look like? Well, when the box is slowing down, like friction applies that kind of force to the box. And so you have a force that's opposite to its motion, that's slowing it down. And so angle 180 degrees is slowing down. That's when you have negative work being done on the box. It's in the opposite direction of the force and of the velocity of the object. Okay, today for homework on page 262, do 4 through 7. On 260, actually, sorry, 4 through 6. On page 262, just do 4 through 6. Yeah, 262, do 4 through 6.